record. Okay, so just from last week, Newton's third law. Collisions are a great example, and we can get some really cool equations from it. In a few weeks' time, we will look at momentum and momentum in collisions. Also, indirectly, weight and normal. I remember indirectly because we've actually got two action-reaction pairs. If you are at rest, and that's what I've said there, if the sum of all forces equals 0, then you are not accelerating. Please be aware, there's two different ways that you can be in equilibrium, at rest or in a constant speed. So if you're sitting in a car and you're cruising along at a constant speed, all of the forces must be balanced. It's only if you are accelerating that the sum of all forces is non-zero. So you can split this next 4 weeks up into two topics, statics and dynamics. Statics is when it's summing to 0. Dynamics is when we've got an accelerating condition or an unbalanced force. All right. Your weight force, key things, you'll see it written slightly differently. I'll try and be consistent in writing it as a capital W. It's equal to mass times gravity. On Earth, at the surface, we're going to take this number. It always acts downwards, and it's always acting. Okay, so when we do questions, you don't have to worry where we are on the Earth, whether we're near sea level or not. Just take that as 9.8. At year 12, we can look at how this value changes as you go up into space. So the astronauts aboard the ISS, they're at about 8.7. Because they're a little bit further away from the Earth, the force of gravity is a little bit weaker where they are. Yes, Matthew?
The sum of all forces will also equal weight plus normal force?
Yes, absolutely. So one thing I skipped, so maybe I'm just going to lasso this and drop it down a bit, is we could write the sum of all forces equals 0 equals weight plus normal. Now, that Greek sigma means the vector sum. It means add vector 1, add vector 2, add vector 3. Okay? It's 1 plus 2 plus 3 plus dot, 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 dot for as many vectors that you have adding. It means the sum of. So I want to see additions. So what we need to say then is if we've got vectors in opposing directions, I want you to include your sign convention. That any vector that's acting upwards is positive and any vector that's acting downwards is negative. You can see then that gravity, I've written it in the wrong order, so let me just reorder this. Weight force I could write as negative plus positive. Okay? So that's the direction of weight, and that is the direction of the normal force. Yes, Cameron?
What page is this?
Don't know.
Second
Page 3.
Page 3. I think you're in the wrong booklet.
Do you have the booklet?
Oh, the second one.
It's just about there.
Well, I don't have any more, so good luck.
Go on, yeah.
We got one last lesson, right? You were here. Come on, Mitch, mate.
Now, friction is another example of Newton's third law. As an object is rolling along a surface, it's going to come into contact with a surface that is sort of perpendicular to its motion, and there will be a little action force pushing forward, and there'll be a reaction force pushing backwards. And so our reaction force is due to the force of friction. Now this can be rolling, so you can have motion, you throw a ball along as it's rolling, there's a backwards force, or it can be an applied force. So for example, I could apply a force of plus 100 newtons, and friction might oppose equal to negative 100 newtons. It's not moving yet, but it's opposing the applied force. So it always opposes, it never acts in the same direction. That would break all of the rules. If you rolled a ball along and it suddenly got faster and faster and faster and disappeared off into the horizon, you would be a little bit perplexed if the surface was horizontal. and there was no motor in the ball. Right? That's not what we see. The reason, as I mentioned, if we could zoom in on the surface, you would see little microscopic irregularities. So no surface is perfectly smooth. We've got these irregularities at the surface, and so they're going to come into contact. If I then try to push with an applied force, then there's going to be regions where we have little action-reaction pairs. Okay? So all of those action-reaction pairs are going to sum together to produce a opposing force. Okay? So you push something forward and you're going to have all of these surfaces that are now into contact. At a true, deep, philosophical, esoteric level, you're looking at trying to push electrons towards other electrons. So the electrons in the surface of the book are coming into contact with the electrons in the surface of the table. And De Pauli came up with this exclusion principle that said that electrons cannot exist in the same position and have the same quantum state. And that's what causes a Coulombic repulsion, electrical repulsion. You could then get really philosophical and say, you're not ever truly touching something, you're hovering above it by a certain amount because the electrons are not able to exist in the same point in space, but they're going to be a little bit above it such that the sum of the electric repulsions, that's the normal force. Okay? Again, we don't need to go that philosophical. This is not really in the syllabus, but it's such an easy thing to look at. There is a limit to how much friction an object can oppose. Eventually, the applied force is greater than friction, the object accelerates. The equation is this. It's your friction force is equal to a coefficient multiplied by the normal force. It's not the weight force. Because you could push down on an object, you end up increasing friction. Have a think. If you push down on your laptop and then try to push it laterally, it's not going to slide as much. You could lift it up slightly. You could have a string and you could pull the laptop up slightly. It's still in contact. The normal force now reduces. It'll slide more readily. Now, one other way to draw this is here is my friction force as a function of my applied force. Now, for a certain point, it's 1-to-1. It's directly proportional. So, for example, I apply 1 Newton and friction goes, yep, I can resist that. I apply 2 Newtons and friction goes, yep, I can apply that. I apply 3 Newtons and friction goes, no, sorry, I can't apply 3 Newtons. There's a limit. And this is called the limit of static friction.
Why does it go up and then down?
Ooh. Well, the idea here is once it's got a little bit of momentum, then it can use that momentum to roll over all of those ridges. So if we imagine when an object's stationary, it's sort of meshed down inside all of those microscopic irregularities of the surface. Once you lift it up and out and start getting that orange surface sliding across, it's got some momentum. It can sort of drift along with its own moving inertia. And so you require less force because it's not actually sinking down into those grooves. This is not in the syllabus, but we could get out a LabQuest with a force meter and we could slowly increase the force and you would see the friction force. Well, actually, you would be measuring the applied force, but it would be building, and then you would see it drop. Once it starts moving, it's then called kinetic friction.
Could we do that?
Yes, but no, we don't have enough time. There's a lot of fun stuff that we could be doing. We just don't have enough time in year 11. Sorry.
What would be an example where that would happen? What would be an example? So you'd be like pushing down on something.
Okay. You want to push a fridge across your kitchen floor. You find that you need to apply 500 newtons to get it going, but once it's sliding, you only need to apply 450. The prowler sled up in the gym, same deal. 500 newtons to get it going. Once it's going, it drops down. Now, this coefficient, if we rearrange for the coefficient, you can see, I didn't do that, you can see that it's equal to a force divided by a force, so it's got no dimensions. It is simply a number between 0 and 1. So you could say mu ranges between 0 and 1, where 0 equals no friction. So think the air hockey table, the air hockey puck drifting along, or that'll do. And 1 is lots of friction.
What's FN? Wait, wouldn't...
Fn, normal force.
Why could it not be more than... Sorry, is that
Yeah, true.
constant
What's
for
also
kinetic
one?
or static?
Typically, if surfaces are in contact without adhering, eventually they will slide. So we're ignoring like stickiness, we're ignoring any adhesive forces due to water, you know, like the suction cups that you can have stuck to your shower wall, you know, little suction darts that you can shoot. That's sort of adhesive. So we're ignoring that, okay? Typically we find that the most grippiest substance would be rubber upon rubber, and in order to get it sliding, you would need to apply a lateral force that's equal to its weight force, or normal force, okay? Typically. So, concrete on rubber is quite a high number. It's around about 0.9. Ice on ice is very low. It's going to be around about 0.05. Metal on wood might be somewhere in between. Again, different surfaces. You're never going to be able to get the same piece of wood and the same piece of metal. It depends on how they're machined. You could zoom in and see that one is slightly rougher than the other. So it's unique to the surface. You could get 5 identical pieces of metal and slide them across the same surface. You might find that the friction values are all slightly different. The coefficients might all be slightly different. So it's empirically measured. You could find some textbooks, some websites do have lists of surfaces, but it varies. Yes,
Are they consistently different?
could be a good investigation for you to pursue,
And also,
but in your own time.
why isn't your, if it goes up 2 but not including 1, or it doesn't go above 1, why isn't your coat slipping off the bench? Bench is pretty slippery. Your coat's definitely not adhering.
Well, it's no, because the friction is not 0. I have to apply some force. I could attach a force probe and figure out how much force is required to get this moving. From that value and knowing the normal force, I could figure out the coefficient.
Also, is the coefficient for kinetic or static?
Good. I like that you have asked that, and for not in the syllabus, but generally your coefficient of static is greater than your coefficient of kinetic. That's what this graph is showing here. It builds, it builds, it builds. That's a highlighter. Try that again. It builds, it builds, it builds, and then it drops down. So again, we could do this experiment with my coat. We would find that the coefficient for its stationary is 0.5. When it's moving, it might drop to 0.4. Meaning I need to get 0.5 of the normal force to get it moving, but only 0.4 of the normal force to keep it moving. Okay? Brady.
Is this whole thing is the equation the unit? Could that be?
If we did include it in a test or an exam, because it's not in the data sheet, I would need to give you the equation and explain what the 3 variables were. Okay? Throw it in a comprehension, throw it in a sys test. Okay? But let's keep moving.
Last question.
So, no more last questions. A 50 kilogram mass is sitting upon a surface. We'll assume horizontal. We've got a coefficient. We've got an applied force. Let's figure out everything. So I'm going to figure out the weight force first. W equals mg equals 50 times negative 9.8 minus 490. From that, I can infer that the normal force is negative weight because it's not accelerating up into the air or down into the ground. So we'll say 490 newtons upwards. I can then find out what the coefficient is. Now, let's just take this as, I think it will start to accelerate, but let's figure out what the friction force is that's going to equal mu n. So we'll go 0.6 multiplied by 490. Okay, I haven't got my solutions out, but I'll quickly... 294 newtons. And now we come along and apply a larger force of 800 newtons. Okay, so with that in mind, remember, I don't know if I said this yesterday or last week, we can split our forces into vertical and we can split them into horizontal. Did we talk about that? The sum of all forces. You don't need to do this, but I just want to show you that the sum of all forces in the vertical is equal to 0. And that's going to be weight plus normal. Let's just check. We get 0 equals minus 490 plus 490. So you could say that the object is in equilibrium in the vertical. It is not accelerating up into the air, and it is not sinking down into the surface. But the same cannot be said for the horizontal. So this is where we then need to go. We can say that the sum of all forces in the x is equal to F applied plus FF. I might assign the convention that my applied force is in the positive direction. So we'll go 800 plus negative 294. And so that makes sense that the friction is going to subtract from the applied force, never add. We get 506. As per my diagram, I've assigned right. Then, let's take Newton's second law. We could say that the acceleration is equal to the net force divided by its mass. So a 506 Newton force acts on a 50 kilogram object, and that will cause the acceleration to be 10.012. Or, well done, 10.01 meters per second squared. Right. Well, what? 10.12. So rounded to 3. Okay. Now.
It's north, isn't it?
Right.
No.
We weren't. Oh, north. Holy moly! Why didn't you pipe up earlier? Oh man. Oh man.
So you're going to start them up.
Okay, now let's suppose there's a limit. Imagine this was a person pushing this box. They're not going to be able to apply that force indefinitely. Because have a think, after 10 seconds they're traveling 100 meters per second. So it's going to cap out. Let's just say that they can apply it for a maximum, or in fact this is going to be, it's unrealistic. It is unrealistic. What I'm saying with this question here, gentlemen, is you can take your force, once you've got acceleration, we can go back to the previous 4 weeks of this topic and do SUVAT. So you could say V equals U plus AT. We'll go 0 plus 10.1 by 1.4. All right, so you can go back and do all of that distance, velocity. It's now traveling at 14.1 meters per second north. Don't worry about the impulsive force. I believe it is just that. That's the force that's unbalanced. And then let's do C. I don't know why I included that. How far? S equals a half AT squared. So it covered a distance of 9.90. Okay. So remember, guys, we can't just forget everything that was learnt in weeks 10, 1, 2, and 3. We're learning a little bit more, and we can then apply it back to our accelerated motion equations. Okay. There's some homework for you to do some other time. Let's get into inclined planes, because this is where the magic happens.
Yes, sir.
Horizontal planes first. Yes, Cameron.
Isn't there some sort of unit of like Newton seconds? 'Cause
Yes, there is, Cameron. It's momentum. Yes, Brady. Yes, Brady. Okay. So, I've stolen this from the physics classroom, a very good website with heaps of diagrams and interactives and question sets that you can have a look at. Net force acceleration. All right, so it's Newton's laws. We've already discussed, if you've got a force, you can resolve it into horizontal and vertical. You're just going to use sine theta and cosine theta. We've also said the acceleration is F divided by M. Okay? A natural extension is now to combine Newton's second law with force vectors that are directed at angles. So let's simplify a difficult problem. This is what we're going to do. Let's look over here first. Now let's say that you've got a box and you're pulling that box upwards, like maybe this is a suitcase that you're dragging along. Well, you're not going to be pulling it directly horizontal, you're not pulling it vertically. Let's say you're pulling it 30 degrees above the horizontal with a magnitude of 80. Okay, so we would need to resolve that vector into x and y. And so you could split this bad boy up into dash, 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 dash. We call that fx, dash, 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 dash. We call that fy. We've got the magnitude, we've got the interior angle, so that would be f sine 30, and then fx would be f cos 30. You can split them apart. The reason we split them apart is because we want to combine the horizontals, and we can combine the verticals using a simple convention. But we've got to split this guy up into how much vertical is it acting and how much horizontal is it acting. Well, the other diagram has done that for us. So you'll notice it split that horizontal applied force. It did 80 sine 30. Turns out that 80 sine 30 is 40 newtons upwards. 80 cosine 30 is a little bit trickier. Turns out that it's 69.3 newtons to the right. Now we've done that, we can look at the verticals. So I'm just going to color code my verticals. And let's just sum the verticals. So right now, oops, that should have been black. The sum of all forces in y, I want you to write the first statement down. You're going to say equals weight plus Fn plus Fay. And I will just highlight. That was a highlighter. Come on, laptop. You can do it. We've got our convention there, so we can now go equals negative 98 plus 58 plus 40 equals 0. So this object is not accelerating up or down. But is it accelerating left or right? Let's have a look. I'm now going to analyze the horizontal. So we've now got left or right, forwards, backwards. Yeah. We'll say right. We'll just assign right as the positive. So sum of all forces in the x equals, we'll go F friction plus FAX. I'll go negative 40 plus 69.3 equals plus 29.3. Boom! There is our unbalanced force. So this object is accelerating. Just turns out it's accelerating off to the right. Okay. Now, have we got... Oh, Jesus Christ almighty. Okay. My laptop is panicking here. This resource is a little bit mean because it hasn't given us the mass. But we know the weight force. So we just have to do a quick side mission to figure out what the mass is. So if we know that weight equals mg, then mass is going to be weight divided by g. So we'll go negative 98 divided by negative 9.8. It turns out it was 10 kilos. So now, again, the logical progression you'll find in these questions is you've got to find what the net force is, then you can determine the acceleration, then you can determine all the SUVAT stuff. All right? So the first thing we've got to do is figure out what's the unbalance and in what direction is it. So now we can do that last step. The acceleration from Newton's second law is F divided by M. Okay. One thing I want you to look at now, we've got the answer, and I think I glossed over it. Without that applied force, that object is just sitting there. You would have weight down, 98, normal up, 98. Now you add an applied force. It's actually doing two things. I need you to follow my logic here. Firstly, we're trying to move the object, and so suddenly friction appears. If you didn't apply the force, friction isn't there. Friction isn't something, you're not going to look at a box on the table and it suddenly goes sliding off and you go, look, friction. No. I'm going to try and push the object or pull the object right. Friction's going to act left. But also, this applied force has a vertical component. So look what happened to the normal force. It's not equal to the weight force, is it? So a big misconception that students have from year 10. In year 10, there's no applied force, and in most scenarios, the normal is just equal and opposite to the weight. But now, I've got another vertical component. And if we need the verticals to sum to 0, if the applied force has an upwards component, then the normal force can reduce slightly. Right? So if you pull that a little bit harder, that goes up a little bit, this will reduce a little bit. Okay? Now, think of the flow-on consequence. Friction is determined by the normal force. So the friction would actually be less because the person is pulling it upwards. By reducing the normal slightly, friction is reduced. So I imagine if we converted this question to just applying a horizontal force, how would the normal force change? It'd be 98. And then what would friction be doing? It would be increasing. If we increase the normal force by a factor of 50% approximately, then I would expect my friction to increase by a factor of 50%. All right, I think I can stop talking now because I'd like you to do exactly the same for these two examples. Again, for some stupid reason, well, they're just asking you to do a little bit more work. You have to find out the maths. Do exactly the same steps. Resolve your forces into vertical and horizontal. Oh, look, they've already done it for you. How kind of them. Our applied force has already been split into its components. And then if you're daring enough, you've got 20 minutes left. Do the next page, do the next page, do the next page. Page 10, 9, and 8. Get going, please.
So if you do end up with an X and a Y force, do you do Pythagoras?
Yeah, and that sucker's accelerating in the direction of the net force. So have a think. If you're really angry at the airport because you missed your connecting flight and you yank on that suitcase so hard, it's going to launch off the ground. You yeet it. You send it.
Surely you'll screen record this.
Yeah, I wish I'd stopped screen recording it. So if you yank on that suitcase so much that the vertical component of the applied force is greater than the weight force, that suitcase is flying up into the air. And we can look at those scenarios. You just have to analyze them using the steps. Okay.